Welcome to Electric Learning's Calculus series. Today, I would like for you to consider, can change occur at an instant? To get into the idea of change at an instant, we will first review a topic you will be familiar with, the average rate of change. To calculate the average rate of change over an interval, we find the slope between the endpoints. Let's think about a real-life situation. Let's say I want to go for a run. I get started at 7:40 a.m. and at 8:25 a.m., I finish my workout having completed 6 miles. If I had a speedometer, like a car, I could at any one instant tell you how fast I was running. However, I am not a car, so I can only calculate my average speed over this section of my run. My average velocity is found taking the difference of my distance, 6 miles minus 0 miles for my start, and by finding the change in time. The difference from 7:40 a.m. to 8:25 a.m. is 45 minutes, or we'll say 3/4 of an hour. To calculate my average rate of change, I take that distance, 6 miles, and divide it by my number of hours, 3/4 of an hour, and we can find the average rate of change is 8 miles per hour. If we think a little deeper on this rate, you might ponder, how fast was I running at 8 a.m.? Just because my average speed was 8 miles per hour does not mean that that is how fast I was running at every instant of my morning workout. So how can the average speed, which we calculated as the change in distance over the change in time, help us find my instantaneous speed at 8 a.m.? At one instant, you aren't traveling a distance, and there's no change in time. We cannot use this slope formula in the same way. That would give us 0 over 0, which we know we cannot simplify. However, what if we thought about making our points that we're calculating this average rate of change with closer to that 8 a.m. time? This is going to be some foundational thinking needed for calculus. Let's take a look at a 1-minute interval around 8 a.m. Maybe like 7:59 a.m. in 30 seconds to 8 a.m. in 30 seconds. Let's say in this 1 minute I traveled 686.4 feet. To calculate my average rate of change over that minute, we would take that distance and divide by 1 minute, or if we wanted to do things in miles per hour, convert that into hours, 1 over 60, and divide. Now, what if we wanted an even better approximation of that speed at 8 a.m.? What if we took an even smaller interval of time? Let's say after 0.1 minute, I traveled 68.6456 feet. Then we could calculate that average speed by taking that distance over the change in time. An even better approximation could be if we were to look at an even smaller amount of time, say 0.01 minutes. Let's say in 0.01 minutes, I traveled 6.86567 feet. Then we could calculate again our average speed, which is getting closer and closer to this one instance of time at 8 a.m. Essentially, we can get a very good approximation for an instantaneous speed by looking at very, very small intervals. Abandoning our running example, let's look at some more mathy things. Let's take a look at a graph of some function f. To find the average rate of change, aka our slope, on the interval from 0 to 5, we would calculate f of 5 minus f of 0 over 5 minus 0. To estimate the instantaneous rate of change at 5, we need 2 points very close to that point at 5. A good approximation for the instantaneous rate of change at 5 might be f of 5.1 minus f of 4.9 over 5.1 minus 4.9. If we want an even closer approximation to the instantaneous rate of change at 5, we could use points like 5.01 and 4.99, seeing the values that the function gives and setting that up into our average rate of change formula. And even better, we could get even closer using 5.001 and 4.999, so on and so forth. You could see these averages getting very, very close to our instantaneous rate of change. Now let's look at a table. Let's see if you can estimate the instantaneous rate of change at t equals 10 from the given table. I'll give you a moment to think. You will notice on the table that we're not given information when t equals 10, so we can't actually find that value at 10. However, if we look at an interval around 10, say using t equals 9 and t equals 11, we can use our average rate of change formula to find a good approximation of our instantaneous rate of change at 10. To wrap up, let's say v of t is a function which gives speed at time t. Are you able to verbalize the meaning of the following? Take a moment, write down some ideas of what you think these 3 things represent. which would be the best estimate of the instantaneous rate of change at time equals 2. For v of 2, that would be our speed when time equals 2. v of 2 minus v of 0 over 2 minus 0 is the average speed over the interval from time equals 0 to time equals 2. And finally, v of 3 minus v of 1 over 3 minus 1 is the average speed over the interval time equals 1 to time equals 3. To answer that last question, the best estimate for the instantaneous rate of change at 2 would be the last one, using our interval over 1 to 3, because 2 is found inside of that interval. In the next video, we will start to explore limits, which will be the building blocks of calculus. Thanks for your consideration.